Look up at the night sky. Between the stars, between the galaxies, you see nothing. Darkness, emptiness, void. But what if I told you that this nothing is actually something? Something vast, something structured, something that holds the entire universe together like a three-dimensional spider's web spanning billions of light years? In 2003, astronomers created a map that changed everything. They plotted the positions of 200,000 galaxies across space. What they saw should have been impossible. Galaxies weren't scattered randomly across the cosmos. They formed patterns, filament, threads of light stretching across the universe, connecting in nodes, wrapping around enormous voids of pure emptiness. The structure was too perfect, too organized, too intentional. This wasn't just an interesting pattern. This was evidence of something fundamental about the architecture of reality itself. A cosmic web woven from invisible threads of dark matter, holding galaxies in place like dewdrops on a spider's silk. What if everything we know about empty space is wrong? What if the void between galaxies isn't empty at all, but filled with an invisible scaffolding that controls the fate of every star, every planet, every atom in existence? Today, we journey through evidence that challenges everything we thought we knew about the structure of the cosmos. In 1986, Margaret Geller and John Hutcher at the Harvard-Smithsonian Center for Astrophysics began an ambitious project. They wanted to map the universe in 3 dimensions, not just where galaxies appeared in the sky, but how far away they were from Earth. For years, astronomers had assumed galaxies were distributed more or less randomly throughout space. Sure, there were clusters, groups of galaxies bound together by gravity. But beyond that, cosmic democracy, random distribution. Geller and Hutcher spent years measuring the redshifts of thousands of galaxies, determining their distance. When they finally plotted their data in 1989, they saw something that made them question their own instruments. A wall. A great wall of galaxies, stretching across 500 million light-years of space. They called it the Great Wall. A sheet of galaxies so vast that light from one end takes 500 million years to reach the other. This wasn't a cluster. This was structure on a scale that shouldn't exist. Here's why this was disturbing. According to our understanding of the Big Bang, the early universe was almost perfectly smooth. Matter was distributed evenly in all directions, with only tiny variations, fluctuations of about 1 part in 100,000. These tiny ripples are visible in the cosmic microwave background radiation, the afterglow of the Big Bang itself. Gravity amplifies these ripples over 60. Dense regions attract more matter. They grow. They form galaxies. Simple enough. But here's the problem. The universe is only 13.8 billion years old. That's how much time gravity has had to work with. And gravity moves at the speed of light. It can't pull matter together faster than that. When you do the math, there simply hasn't been enough time for gravity to create structures 500 million light-years across. The universe isn't old. The Great Wall shouldn't exist. Yet there it was, visible in their data, impossible to deny. As more surveys mapped more galaxies through the 1990s, the pattern became undeniable. The universe wasn't just showing large structures here and there. The entire cosmos was organized into a vast web. Imagine a kitchen spot. The solid parts represent where galaxies cluster, along filaments, in sheets, at the intersection points we call nodes. The holes represent voids, enormous bubbles of empty space where almost no galaxies exist. This is the 2-degree field galaxy redshift survey, completed in 2003, mapped 245,000 galaxies. The Sloan Digital Sky Survey has now cataloged. Every new survey confirms the same pattern. The universe is organized like a vast three-dimensional neural network, with matter concentrated along threads connecting at nodes surrounding vast empty voids. The largest of these voids stretches nearly 2 billion light-years across. A bubble of emptiness so vast that light from the Big Bang has been traveling since the universe began and still hasn't crossed it. Think about a region of space where, if you floated at the center, you could look in any direction and see almost nothing for a billion light-years. No galaxies, no stars, just darkness. The cosmic web raises a fundamental question. How did this structure form? Random distribution doesn't create patterns. Gravity alone doesn't explain filaments stretching across a billion light-years. And there hasn't been enough time since the Big Bang for matter to organize itself this way through normal gravitational attraction. Something else must be involved, something that acted like a template, a scaffolding upon which normal matter could gather and condense. Scientists realized they were looking at the shadow of something invisible, something that makes up most of the mass in the universe, something we call dark matter. But the evidence forces us to confront an uncomfortable possibility. What if dark matter isn't just invisible particles scattered through space? What if dark matter itself is organized into this cosmic web, and everything we see, every galaxy, every star, every planet, is just decoration on an invisible structure that was already there? The first clue came from how galaxies move. In the 1970s, Vera Rubin discovered that galaxies rotate too fast. Stars at the edges of galaxies orbit at speeds that should fling them into intergalactic space, yet they stay in place. Something invisible was holding them in. That something was dark matter, an invisible mass providing extra gravitational pull. But here's what's remarkable. When astronomers mapped the velocities of thousands of galaxies across large regions of space, they found something unexpected. Galaxies aren't just moving randomly. They're flowing along preferred directions, streaming along the filaments of the cosmic web toward the nodes where filaments intersect. It's as if galaxies are sliding down invisible rails, channeled along predetermined paths by something we cannot see. The Cosmic Flows Project, led by Brent Tully, has mapped these velocity patterns across hundreds of millions of light-years. The data is clear. Galaxies are being shepherded by the underlying structure of dark matter. Einstein's theory of general relativity tells us that mass bends space. Light traveling through bent space follows curved paths. This means that massive objects act as gravitational lenses, distorting the images of objects behind them. In 2012, astronomers pointed the Hubble Space Telescope at a seemingly empty region of space between two galaxy clusters. They were looking for something extraordinary, the filament connecting them. They found it. The combined mass of dark matter in the filament bent the light from galaxies billions of light-years beyond it. By carefully measuring how that light was distorted, astronomers could map the invisible filament. It was there, a thread of dark matter stretching across 60 million light-years of space, exactly where the cosmic web predicted it should be. This wasn't inference. This was direct observation of the invisible scaffolding. The cosmic microwave background, the CMB, is the oldest light in the universe. Released 380,000 years after the Big Bang, it shows us what the universe looked like before the first stars formed. The Planck satellite, which observed the CMB with unprecedented precision from 2009 to 2013, revealed something crucial. The tiny temperature fluctuations in the CMB aren't random. They show patterns, specific scales where fluctuations are stronger. These patterns match exactly what we'd expect if dark matter had already begun forming the cosmic web in the early universe. The seeds were planted in the first moments after the Big Bang, imprinted into the fabric of space itself. When cosmologists run computer simulations starting from these initial conditions and let gravity work forward through dying, they get the cosmic web every time. The simulations match the observations with stunning precision. The structure we see today was predetermined by the initial conditions of the universe itself. Here's a puzzle that connects directly to the cosmic web: the missing baryons problem. Baryons are ordinary matter, protons, neutrons, the stuff that makes up atoms. When we count up all the baryons in stars and galaxies, we only account for about 10% of the baryons that should exist based on Big Bang nucleosynthesis. Where are the other 90%? For decades, astronomers suspected they were hiding in the cosmic web, specifically in the warm hot intergalactic medium, or WHIM. This is a diffuse plasma of gas, heated to temperatures between 100,000 and 10 million degrees, too hot to form stars, but too cool to emit X-rays efficiently. In 2018, two independent research teams found them. Using X-ray telescopes to observe distant quasars, they detected absorption lines from highly ionized oxygen that had lost most of its electrons, a signature of the WHIM. The missing baryons were threaded along the filaments of the cosmic web, exactly where theory predicted. The invisible scaffolding of dark matter had trapped ordinary matter in its threads, heating it through gravitational compression as it fell into the filaments. But this represents just one piece of a much larger puzzle. The cosmic web isn't static. It's alive, growing, evolving, changing over. Computer simulations show that in the early universe, the web was subtle, thin filaments connecting small nodes. As I'd progressed, gravity amplified the structure. Filaments grew thicker as more matter fell into them. Nodes became denser, transforming into the galaxy clusters we see today. The voids expanded. As matter drained out of underdense regions into filaments and nodes, the voids grew larger and emptier. We're watching this happen in real time. Observations show that galaxy clusters are still growing, accreting matter from surrounding filaments. The Coma Cluster, one of the largest structures in the nearby universe, contains thousands of galaxies and is still pulling in new members from the surrounding web. But here's what's disturbing. The web is becoming more extreme. Rich regions are getting richer. Voids are becoming emptier. The universe is segregated. Matter is concentrating in an ever smaller fraction of space, leaving vast regions increasingly devoid of anything. Speaking of voids, they're strange places. In 2013, astronomers discovered something unexpected. The voids aren't completely empty. A few sparse galaxies drift through them, lonely island universes separated by hundreds of millions of light-years from their nearest neighbors. These void galaxies are different. They're typically smaller, bluer, and forming stars more actively than galaxies in dense regions. They evolve in isolation, undisturbed by the gravitational harassment that galaxies experience in clusters. But the most remarkable discovery involves the expansion of space itself. Inside voids, space expands faster than average. The lack of matter means less gravitational pull to slow expansion. This means that voids are growing faster than the cosmic web can keep up with. The universe isn't just expanding, it's fragmenting, breaking apart into increasingly isolated islands of structure surrounded by growing oceans of nothingness. Now we arrive at one of the cosmic web's greatest mysteries. In 1986, astronomers discovered that our Milky Way galaxy, along with thousands of neighboring galaxies, is being pulled towards. Our local group of galaxies is moving at 600 kilometers per second relative to the cosmic microwave background. Not because they're weak, but because they've lost specific muscle patterns that nobody talks about. The researchers it lies beyond the galactic plane of the Milky Way, hidden behind dust and stars. But by mapping galaxy velocities, astronomers traced its location, about 250 million light-years away, in the direction of the Centaurus and Norma constellations. When X-ray and infrared telescopes finally pierced the obscuring dust, they found it an enormous concentration of mass, equivalent to tens of thousands of galaxies, forming a massive node in the cosmic web. But here's the twist. The great attractor itself is being pulled towards something even. The Shapley supercluster, the most massive structure in our cosmic neighborhood, containing more than 8,000 galaxies. We're witnessing the hierarchy of the cosmic web. Nodes connect to larger nodes. Filaments feed into trunk filaments. The structure is fractal, similar patterns repeating at different scales. In 1998, astronomers made a discovery that changed everything we thought we knew about the fate of the universe. The expansion of space is accelerating. Something with negative pressure, something we call dark energy, is pushing space apart. It makes up about 68% of the total energy density of the universe. This has profound implications for the cosmic web. In regions of high-density galaxy clusters and the nodes of the web, gravity overwhelms dark energy. The structure holds together. But in lower-density regions, the filaments, and especially the voids, dark energy wins. Space expands faster. The cosmic web is being stretched. Filaments are thinning. The distance between nodes is increasing. Computer simulations of the far future show something haunting. Eventually, each node will become completely isolated. The light from other nodes will be redshifted to infinity. Each cluster will become its own island universe, unable to see or interact with any other structure. The evidence extends beyond the observable cosmic web into the realm of cosmic destiny itself. A future where structure fragments into isolated islands in an infinite ocean of expanding void. To understand the cosmic web, we need to understand dark matter itself. The leading theory is called lambda CDM. Lambda for dark energy, CDM for cold dark matter. Cold means the dark matter particles were moving slowly when structure began to form, allowing gravity to collect them efficiently. According to this model, dark matter consists of particles that interact only through gravity. They don't emit light, they don't absorb light. They pass through ordinary matter, like ghosts. The only way we know they exist is through their gravitational effects. In the first moments after the Big Bang, quantum fluctuations in the inflation field created tiny variations in density. As the universe expanded, these variations became imprinted in both dark matter and ordinary matter. But here's the key. Dark matter decoupled from radiation much earlier than ordinary matter. While ordinary matter remained coupled to photons, locked in a plasma that smoothed out structures, dark matter was free to start collapsing under its own gravity. By the time ordinary matter finally decoupled from radiation at 380,000 years after the Big Bang, dark matter had already formed the scaffolding of the cosmic web. Ordinary matter simply fell into the gravitational wells created by dark matter, collecting along the pre-existing filaments. The honest answer: we don't know. The leading candidate is WIMPs, weakly interacting massive particles. These would be subatomic particles left over from the Big Bang with masses 10 to 1,000 times heavier than a proton. Billions pass through your body every second without interaction. Despite decades of searching with increasingly sensitive detectors buried deep underground, we haven't detected them directly. Not yet. Alternative theories: maybe dark matter is axions, extremely light particles predicted by certain extensions of particle physics. Maybe it's primordial black holes, tiny black holes formed in the early universe. Maybe it's something we haven't imagined yet. What we do know is what dark matter does. It forms structure. It gravitationally herds ordinary matter. It holds galaxies together. It shapes the cosmic web. At the University of Durham, the EAGLE simulation, one of the most sophisticated cosmological simulations ever run, tracked the evolution of millions of dark matter particles from the Big Bang to the present day. The results? A cosmic web nearly indistinguishable from what we observe. The details differ between models of what dark matter is, but the cosmic web emerges in all of them. The structure is robust, predictable, perhaps inevitable. Some physicists question whether dark matter exists at all. Modified Newtonian dynamics, or MOND, suggests that gravity behaves differently at very low accelerations. Instead of invisible matter, perhaps we need new physics. Mondeir explained galaxy rotation curves without dark matter, but it struggles with the cosmic web. It cannot explain gravitational lensing observations. It cannot explain the patterns in the cosmic microwave background. It cannot explain why the cosmic web looks exactly like what cold dark matter simulations predict. The evidence overwhelmingly favors dark matter's existence. The cosmic web might be the strongest evidence of all. A vast structure that emerges naturally from dark matter physics but requires elaborate fine-tuning in alternative theories. This forces us to reconsider fundamental assumptions about the nature of matter itself. Most of the universe is made of something we cannot see, touch, or detect, except through gravity. And that invisible substance determines where every visible galaxy forms. The next generation of telescopes will map the cosmic web in unprecedented detail. The Rubin Observatory in Chile, beginning operations in 2025, will survey the entire southern sky every few nights for 10 years. It will discover and track billions of galaxies, mapping the cosmic web with extraordinary precision. The Nancy Grace Roman Space Telescope, launching in 2027, will use gravitational lensing to map dark matter directly, including the filaments of the cosmic web, across vast swaths of the universe. The Square Kilometre Array, a radio telescope with thousands of antennas spread across Australia and South Africa, will map the distribution of neutral hydrogen gas along the cosmic web's filaments, revealing the bridge of ordinary matter between galaxies. These observations will answer crucial questions. How thick are the filaments? How much mass do they contain? How does gas fall into them? How do galaxies form along them? Here's something we've recently discovered. The cosmic web has magnetic. In 2014, astronomers detected faint radio emission from filaments connecting galaxy clusters. This emission comes from electrons spiraling around magnetic field lines. The filaments are magnetized. Where did these magnetic fields come from? They're far too weak to have been generated by stars or galaxies. They must be primordial, created in the early universe, or through processes we don't yet understand. These magnetic fields affect how gas flows along filaments. They channel plasma, they accelerate cosmic rays, they may even affect how galaxies form along the cosmic web. Recent simulations suggest that magnetic fields follow the filaments, threading the entire cosmic web with invisible lines of force. The universe isn't just held together by gravity, it's wired with magnetic fields running along its structural elements. Your location in the cosmic web determines your fate. Galaxies in the dense nodes, galaxy clusters, experience constant harassment. They collide with neighbors. They pass through hot gas that strips away their own gas. They're pulled and distorted by tidal. The result? Cluster galaxies are typically red and dead, old elliptical galaxies that exhausted their gas supplies long ago and no longer form stars. Galaxies along filaments experience intermediate conditions. They receive steady streams of gas flowing along the filaments, which fuels ongoing star formation. But they also experience more interactions than isolated galaxies. Galaxies and voids evolve in splendid isolation. They retain their gas. They form stars steadily. They're undisturbed by neighbors. The cosmic web isn't just structure, it's destiny. Your position in the web determines your evolutionary path, your star formation history, your ultimate fate. Our Milky Way resides in a relatively sparse region on the edge of a filament. We're fortunate. Not isolated enough to be alone, not dense enough to be harassed. Our position in the cosmic web may have been ideal for the evolution of complex life. The cosmic web is also our best laboratory for studying dark energy. By precisely measuring how the cosmic web evolves over time, how filaments thin, how voids expand, how clusters grow, we determine the properties of dark energy with unprecedented accuracy. Is dark energy constant over V, or does it change? Is it Einstein's cosmological constant, or something more exotic? The future evolution of the cosmic web will tell us. Recent breakthroughs suggest that by mapping the cosmic web at different epochs in cosmic history, we might detect subtle changes in dark energy's properties. The Euclid mission, launched by the European Space Agency in 2023, is currently surveying billions of galaxies to create a three-dimensional map of the cosmic web across the past 10 billion years. What we learn could determine whether the universe expands forever, whether the acceleration continues, or whether dark energy might someday reverse and bring everything crashing back together. The cosmic web holds the answer. Here's a disturbing question. Does the cosmic web resemble something more familiar than we'd like to admit? In 2012, a team of neuroscientists and astrophysicists compared images of the cosmic web to images of neural networks in the human brain. The similarities were startling. Both show a network structure with nodes connected by filaments. Both show similar statistical properties in how they're organized. Both show information, whether in the form of neural signals or gravitational influences, propagating along the network connections. This doesn't eat the universe's conscious, of course. It means that network structures emerge naturally when you have nodes connected by efficient pathways. Evolution discovered this principle. Cosmology discovered it independently. But the comparison raises fascinating questions. Information does flow along the cosmic web, in the form of matter, light, gravitational waves. Could complex patterns emerge from this information flow? Could the structure itself encode information about the universe's history? The cosmic web played a crucial role in the universe's earliest moments of light. The first stars formed about 100 million years after the Big Bang. But they didn't form randomly. They formed along the filaments of the cosmic web, in the densest regions where dark matter had collected the most hydrogen, and these first stars were massive, hundreds of times the mass of our sun. They burned brilliantly but briefly, exploding as supernovae after just a few million years. Their explosions enriched the surrounding gas with heavy elements, seeding the cosmic web with the ingredients for planets and life. The James Webb Space Telescope has recently captured images of galaxies from this era, the cosmic dawn, showing how they cluster along filaments, just as theory predicted. We're watching the cosmic web come to life, seeing the moment when the dark scaffolding became illuminated by the first stars. Without the cosmic web, structure formation would have taken much longer. The universe would have remained dark for billions of years. The cosmic web accelerated cosmic history. The cosmic web we observe extends about 13 billion light-years in all directions, the distance light has traveled since galaxies first formed. But the universe is much larger. Inflation theory suggests the total universe is at least 10 to the 23rd power times larger than the observable universe. The cosmic web continues far beyond our horizon, forming structures we will never see. Moreover, as the expansion of space accelerates, our observable universe will eventually shrink. Distant regions of the cosmic web are already protesting. That simple flight of stairs that you once bounded up two at a time now feels like Mount Everest. But here's what nobody tells you about aging in stairs. The researchers discover eventually they'll cross a boundary, the cosmological event horizon, beyond which we never communicate with them, even in principle. The cosmic web is fragmenting not just spatially but causally. Regions that were once part of the same connected structure are being separated forever by the expansion of space. The most profound implications emerge when we consider that the cosmic web we observe is just a tiny sample of a structure that extends infinitely in all directions. A web without end, holding universes of galaxies in patterns we'll never witness. We are creatures of the cosmic web. The atoms in your body were forged in stars that formed along cosmic web filaments. The galaxy you inhabit was born in a node of the web. The very fact that the universe has structure, That it's not just a featureless fog of evenly distributed matter is because of the cosmic web. Without it, no galaxies, no star, no planets, no life. We're not just in the cosmic web, we're of it, products of its structure, shaped by its evolution, destined to follow its fate. Every photon that reaches your eye, every atom you breathe, traveled along the pathways defined by the cosmic web. You are connected, through invisible threads of gravity and history, to structures billions of light years away. The web is the context of everything. We began with a simple observation: galaxies form patterns. What we've discovered is that these patterns reveal the deepest structure of the cosmos, an invisible web of dark matter, seated in the first moments after the Big Bang, holding everything together across billions of light years. The cosmic web is real. It's observable. It's inevitable. It formed from quantum fluctuations smaller than an atom and grew to span the observable universe. It shaped cosmic history, determined where galaxies formed, and influenced the evolution of every structure we see. Yet mysteries remain. What is dark matter? How will dark energy affect the web's future? Could life exist along the filaments, in regions we've never observed? Does the web encode information about the universe's beginning? The current scientific consensus is clear. The cosmic web is the fundamental large-scale structure of the universe. It's not just where matter happens to be, it's where matter had to be given the initial conditions of our universe. As we peer deeper into space and further back in time, we'll continue mapping this cosmic architecture, understanding how it formed, predicting how it will evolve. But the most important realization is this: the universe isn't chaos, it's architecture, structure, pattern. Empty space isn't empty. It's woven together by invisible threads into the most magnificent structure we've ever discovered. A cosmic web that connects everything to everything else, from the smallest galaxy to the largest supercluster, across the entire visible universe. We are part of that web. We always have been. The universe is vast. The mysteries are endless. The journey continues. Part 2. Extended exploration. Now that we understand the cosmic web's basic structure, let's explore its physics in greater depth. The filaments of the cosmic web aren't uniform tubes of matter. They're dynamic, turbulent structures where dark matter and ordinary matter interact in complex ways. Computer simulations reveal that dark matter flows along filaments at speeds of hundreds of kilometers per second. It's not static. It's streaming, creating what astrophysicists call cold flows. These are rivers of dark matter, channeling mass from voids toward nodes. But here's what's remarkable. Ordinary matter follows these flows. Hydrogen and helium gas fall into the gravitational wells created by dark matter, accelerating as they descend. As the gas flows converge and collide within filaments, they heat up through shock waves and the Illustris simulation, run at MIT, tracked the temperature distribution along cosmic web filaments. The results showed a remarkable gradient. Gas enters filaments relatively cool, around 10,000 degrees Kelvin. As it flows toward nodes, it heats to millions of degrees. This heating has profound consequences. It determines what kind of structures to form along the filaments, where stars can ignite, and ultimately where galaxies can grow. In 2019, astronomers using the XMM Newton X-ray telescope detected something extraordinary: a shock wave in the intergalactic medium along a cosmic web filament. Shock waves occur when gas flows faster than the speed of sound. In the cosmic web, multiple gas streams converge from different directions, colliding at supersonic speeds. The collisions create shock fronts, boundaries where gas is abruptly compressed and heated. These shocks are crucial because they change the gas's properties. Before the shock, gas could cool efficiently, collapse, and form stars. After the shock, the gas is too hot. It emits its energy as X-rays and takes billions of years to cool down. This creates a dichotomy in the cosmic web. In some regions, gas cools rapidly and forms galaxies. In others, gas stays hot and diffuse, contributing to the warm-hot intergalactic medium but never condensing into stars. The location and strength of these shocks determine the distribution of galaxies along filaments. Observations from the Chandra X-ray Observatory show that galaxies cluster at specific distances along filaments, precisely where simulations predict cooling shocks should occur. The cosmic web doesn't just passively hold matter, it actively processes it, determining what can form and where. Galaxy formation isn't a one-way street. Galaxies affect their environment, and this feedback reshapes the cosmic web itself. When massive stars explode as supernovae, they inject enormous amounts of energy into surrounding gas. When supermassive black holes at galaxy centers accrete matter, They launch powerful jets and winds that can heat gas millions of light years away. This feedback energy flows back along cosmic web filaments. Recent observations with the Atacama Large Millimeter Array ALMA have detected winds from distant galaxies streaming along filaments, carrying enriched gas containing carbon, oxygen, nitrogen, and heavier elements away from galaxies and into the wider cosmic web. The implications are staggering. The cosmic web isn't just the scaffolding for galaxies, it's a circulatory system. Matter flows in along filaments, forms stars and galaxies at nodes, then gets expelled back into the web, enriched with heavy elements. This process, called galactic recycling, means that gas undergoes multiple cycles of accretion and ejection. The hydrogen in your body might have fallen along a cosmic web filament, formed stars in a galaxy, been expelled in a supernova wind, drifted through the intergalactic medium, and repeated the process several times before ending in the molecular cloud that formed our solar system. We are made of recycled stardust, transported through the universe along the highways of the cosmic web. In 2015, astronomers made a peculiar discovery. Galaxies aren't oriented randomly relative to the cosmic web. Spiral galaxies tend to have their disks aligned with the filaments they inhabit, spinning parallel to the filament's axis. Elliptical galaxies show different patterns, with their major axes often perpendicular to filaments. This alignment is evidence of tidal force, the differential gravitational pull across extended objects. As a proto-galactic cloud falls into a filament, the tidal forces from the filament's mass distribution stretch and align it. The Sloan Digital Sky Survey analyzed the orientations of hundreds of thousands of galaxies and confirmed the pattern. Galaxies remember their formation history. Their spins and shapes encode information about the cosmic web structure they formed within. But the alignment goes deeper. Even the angular momentum of galaxies, the direction they rotate, shows correlations with the large-scale structure. Neighboring galaxies along filaments tend to have correlated spins, suggesting they acquired their angular momentum from the same large-scale tidal field. The cosmic web doesn't just tell galaxies where to form, it tells them how to spin. Here's where things get abstract but profound. The cosmic web defines the topology of the universe at large scales. Topology is the mathematical study of shape and connectivity, which points are connected to which other points. In a universe with random structure, any two points would be connected by roughly similar paths. You could travel in any direction and eventually reach any destination with similar difficulty. But the cosmic web creates a preferred topology. The easiest paths through the universe follow the filaments. Travel perpendicular to filaments, across voids, is possible but far less common for matter flows. This creates what mathematicians call a network topology. The universe has preferred pathways, like a transportation network with highways, filaments, intersections, nodes, and rural areas voids. Recent work applying network theory to the cosmic web has revealed surprising properties. The web shows small world characteristics similar to social networks or the internet. Despite the universe's vast size, typical paths connecting any two nodes through the web are surprisingly short when measured along filaments. The cosmic web gives the universe a structure that's more connected, more accessible than random distribution would allow. This raises a fascinating possibility. If the universe contained intelligence at cosmic scales, civilizations communicating across intergalactic distances, they would naturally communicate along the filaments, using the cosmic web as a communication network. The structure of the universe facilitates connection. Let's turn our attention closer to home, and to one of the cosmic web's most disturbing mysteries. The Milky Way sits on the edge of the local void, also called the KBC void, one of the largest voids in our cosmic neighborhood, stretching approximately 2 billion light-years across. In 2013, Amy Barger and her colleagues at the University of Wisconsin-Madison mapped this void in detail. What they found was troubling. Our position is unusual. We sit near the edge of this enormous underdensity, looking out into a region where galaxies are 20% less common than the cosmic average. This has implications. The expansion rate of space should be slightly faster in our local region because there's less matter to gravitationally slow it down. When we measure the Hubble constant, the rate of cosmic expansion, we might be getting a biased measurement because of our position in the cosmic web. This could explain one of modern cosmology's biggest problems, the Hubble tension. Different methods of measuring the expansion rate give different answers. Local measurements, using nearby supernovae, give a value of about 73 kilometers per second per megaparsec. Measurements from the cosmic microwave background give about 67 Could our position in the cosmic web be skewing our local measurement? Are we misreading the universe's expansion rate because we live in an atypical location? The possibility is being actively researched. If true, it would mean that our view of cosmic expansion, one of the most fundamental properties of the universe, has been distorted by the accident of where we formed within the cosmic web. In 2017, astronomers discovered something that shouldn't exist according to conventional thinking: the dipole repeller. We've known about the great attractor pulling our local galaxies in one direction, but a team led by Yehuda Hoffman at the Hebrew University of Jerusalem discovered that we're also being pushed from behind. The dipole repeller is an enormous void, comparable in size to the local void, sitting on the opposite side of the sky from the great attractor. It's repelling us, not through some mysterious repulsive force, but through absence. The lack of matter creates a gravitational gradient that pushes galaxies away. Think of it like this. Imagine you're floating in a pool with someone at each end. One person grabs you and pulls. That's the great attractor. But simultaneously, the other person pushes the water, creating a current that also moves you toward the first person. That's the dipole repeller. This push-pull dynamic reveals something profound. Voids aren't. They actively shape galaxy flows, creating repulsion through absence, just as matter concentrations create attraction through presence. The cosmic web doesn't just tell us where matter is, it tells us where matter isn't. And that negative information is just as important for understanding cosmic dynamics. In 2013, astronomers discovered something that violates our theoretical expectations: the Hercules Corona Borealis Great Wall. This structure stretches across more than 10 billion light-years, nearly 10% of the observable universe's diameter. If you could travel at the speed of light, it would take you 10 billion years to cross it. Here's the problem: it shouldn't exist. According to the cosmological principle, the universe should be homogeneous at large scales. No structures should be larger than about 1.2 billion light-years. That's a theoretical limit based on how far matter could have traveled and clustered since the Big Bang. The Hercules Corona Borealis Great Wall is 8 times larger than it should be. Either our understanding of structure formation is incomplete, or this structure is a statistical fluke, an extremely unlikely alignment of smaller structures that coincidentally appears as one enormous wall. Follow-up studies have been inconclusive. Some analyses suggest the structure might not be real. It could be an artifact of how we map galaxy distributions. Others maintain it's genuine but requires new physics to explain. Whatever the truth, it reminds us that the cosmic web still harbors mysteries that challenge our most fundamental theories. The cosmic microwave background contains an anomaly called the CMB cold spot, a region about 70 degrees across, where the temperature is slightly cooler than surrounding areas. At first, that seemed like random statistical noise. But in 2015, astronomers discovered something intriguing. There's a supervoid in that direction, an enormous region of the cosmic web with fewer galaxies than expected, stretching about 2 billion light-years. The connection is this: as cosmic microwave background photons travel through voids, they lose energy through a process called the integrated Sachs-Wolf effect. Large voids can create cold spots in the CMB. But here's the mystery: the supervoid isn't large enough to fully explain the cold spot's magnitude. According to our models, the void should create a cold spot only about half as cold as observed. Either the void is more extreme than we thought, or something else is contributing to the cold spot. Perhaps a combination of multiple voids along the same line of sight, or a new physical process we haven't considered. Some physicists have proposed exotic explanations: a collision with another universe, a topological defect from the early universe, or even evidence that our universe might have a preferred direction, violating the cosmological principle's assumption of isotropy. The cold spot remains one of the cosmic web's most perplexing anomalies. And speaking of cosmic anomalies, we must address what cosmologists half-jokingly call the axis of evil. When analyzing the cosmic microwave background's temperature fluctuations, cosmologists break them down into multi-pole components: large-scale patterns, medium-scale patterns, and small-scale patterns. The largest scales should be randomly oriented with respect to any particular direction in space. But they're dark. The quadrupole and octupole moments, the largest scale patterns, align with each other. And they align with something else: the plane of the solar system and the equinox of Earth. This should be impossible. The cosmic microwave background formed 13.8 billion years ago, long before the solar system existed. There's no physical mechanism that could create a connection between cosmic structure and Earth's orientation. Most physicists believe this is a statistical coincidence. We're selecting for patterns because humans are pattern recognition machines. With enough data, unlikely coincidences are inevitable. But a minority entertains more radical possibilities. Could this alignment hint at a cosmological anisotropy, a preferred direction in the universe? Could it suggest our cosmological models are missing something fundamental? Or, in the most extreme interpretations, could it hint that the structure we observe is influenced by observation itself? A controversial suggestion from certain interpretations of quantum mechanics extended to cosmological scales? The axis of evil remains unexplained. A reminder that in our most comprehensive maps of the cosmic web contain patterns we don't fully understand. Until now, we've discussed the cosmic web as lifeless structure, matter and energy arranged by gravity. But what about life? How does the cosmic web affect the possibility of biological The concept of galactic habitable zones, regions within galaxies where conditions favor life, is well established. You can't be too close to the galactic center, where radiation and stellar density are dangerous. You can't be too far out, where heavy elements are scarce. But there's a larger-scale cosmic web habitable zones. Life requires heavy elements, carbon, oxygen, nitrogen, iron, created in stars and distributed through space by supernovae. The cosmic web determines where this enrichment occurs. Regions along active filaments, where gas flows efficiently and star formation is sustained, become enriched more quickly than isolated void regions. In 2018, a team at the University of Durham analyzed the metallicity, heavy element abundance, of galaxies as a function of their position in the cosmic web. They found a clear gradient: galaxies in nodes and along filaments are more metal-rich than galaxies in voids. This means life-friendly chemistry develops faster in certain regions of the cosmic web than others. But there's a complication. Nodes are too extreme. Galaxy clusters experience so many interactions and have such hot intergalactic gas that many member galaxies stop forming stars. They become quenched. No new stars means no new planets, no opportunities for life. The sweet spot might be intermediate density regions along filaments, places like where the Milky Way resides. Enough activity to ensure chemical enrichment, but not so much chaos that planetary systems get disrupted. The cosmic web doesn't just determine where galaxies form. It determines where life-friendly galaxies could exist. The rare Earth hypothesis, proposed by Peter Ward and Donald Brownlee, suggests that while simple life might be common, complex life requires an unusual combination of circumstances. The cosmic web adds another layer to this argument. Complex life on Earth took 4 billion years to evolve. That required a stable planetary environment for an immense duration. But stability isn't guaranteed. It depends on your location. Galaxies and clusters undergo frequent close encounters. Tidal forces disturb stellar orbit. Close passes by other stars could destabilize planetary systems. The Oort cloud, our solar system's reservoir of comets, could get disrupted, sending comets raining into the inner solar system and bombarding Earth. Galaxies in voids evolve more slowly. They're isolated, but they also experience slower chemical evolution. Heavy elements arrive later. The time window for complex life to emerge might be compressed. Galaxies along filaments, like the Milky Way, strike a balance. They receive enough enrichment to develop life-friendly chemistry relatively early, but experience relatively few violent interactions. Moreover, the Milky Way's position on the edge of the local void might be significant. We're somewhat isolated, but not too isolated. We can observe the cosmic web's structure clearly because we're now embedded in a dense region where dust and nearby galaxies would obscure our view. Could it be that intelligent civilizations tend to develop in galaxies positioned like ours, along filaments, near voids, in quiet regions of the cosmic web? If so, the distribution of intelligent life might follow the structure of the cosmic web itself. If intelligent civilizations exist throughout the universe, could they communicate across the cosmic web? The distances are staggering. The nearest node in the cosmic web, beyond our local group, is tens of millions of light years away. Even at the speed of light, communication would take tens of millions of years per message. Civilizations would rise and fall in the time it takes to receive a reply. But perhaps advanced civilizations think in longer timescales. Perhaps they build communication networks that operate across millions of years, with messages propagating along filaments, relay stations at nodes, creating a galactic internet spanning the cosmic web. This idea isn't as far-fetched as it sounds. Recent proposals for lurker probes, autonomous spacecraft that observe and relay information across interstellar distances, could be extended to cosmic web scales. A sufficiently advanced civilization could seed the web with self-replicating probes that establish a communication network over millions of years. If such a network exists, where would we look for it? Along the filaments, where communication would be easy. At the nodes, where multiple civilizations might establish meeting points. The search for extraterrestrial intelligence. SETI has traditionally focused on nearby stars, but perhaps we should also be monitoring directions along cosmic web filaments, looking for signals propagating along the natural communication highways of the universe. Here's a radical possibility. What if life itself propagates along the cosmic web? The panspermia hypothesis suggests that life might travel between planets or even between star systems. Microorganisms could survive in dormant states within asteroids or comets, hitching rides on natural spacecraft. In 2018, experiments aboard the International Space Station demonstrated that certain bacteria can survive years of exposure to space. Some tardigrades, microscopic animals, can survive even longer. If life can survive interplanetary journeys, could it survive intergalactic journeys? The idea seems absurd. The distances are millions of light years, the travel times millions of years. But consider, bacterial spores can remain viable for millions of years in dormant states. Some organisms can survive repeated freezing and thawing, radiation exposure, vacuum conditions. Material does travel along the cosmic web. Gas flows along filaments. Supernovae eject material at speeds approaching the speed of light. Material ejected from one galaxy could, in principle, eventually reach another galaxy along the same filament. If even a tiny fraction of this material contained dormant life, then life could propagate along cosmic web filaments, seeding galaxies throughout connected regions of the web. This would mean life isn't isolated to individual planets or even individual galaxies. It could be a cosmic web phenomenon, arising once in some location, then spreading along the web structure, creating a connected biosphere spanning multiple galaxies. It's speculative, but it transforms how we think about life's distribution. If life propagates along the web, then the cosmic web isn't just the structure of matter. It's the structure of life itself. The anthropic principle states that we observe the universe we do because if it were substantially different, we wouldn't exist to observe it. Applied to the cosmic web, if the web were structured very differently, if filaments were too sparse, or nodes too dense, or voids too large, the conditions for life might not exist. Consider the alternatives. If the cosmic web were much more uniform, matter spread evenly with no filaments, galaxies would form much more slowly, if at all. The universe would remain a diffuse fog of hydrogen and helium for far longer. If the web were much more concentrated, all matter collapsed into a few enormous nodes. The environment would be too violent for stable planetary systems. Radiation levels would be lethal. Close encounters would be frequent. The cosmic web's structure sits in a narrow range that permits life. Not too uniform, not too concentrated. Just structured enough to create galaxies, but not so structured that those galaxies can't harbor stable planetary systems. Why this particular structure? The cold dark matter model, with specific parameters for dark matter properties and initial density fluctuations, naturally produces this structure. But those parameters could have been in a multiverse scenario, where different regions of space have different physical constants and initial conditions. Most universes might not have cosmic webs suitable for life. We exist in this universe, observing this particular cosmic web because it's one of the rare structures that permits observers to exist. The cosmic web isn't just where we live. It's a structure that makes our existence possible, a Goldilocks architecture of matter, energy, and space that creates conditions for complexity, chemistry, and ultimately consciousness. We've discussed how dark energy causes cosmic acceleration. Now let's trace the implications forward to the ultimate fate of the cosmic web. In 2012, Lawrence Krauss and Robert Scherer published a paper titled The Return of a Static Universe and the End of Cosmology. Their calculations revealed something disturbing about the far future. As dark energy continues accelerating the expansion of space, regions of the cosmic web will become increasingly isolated. Currently, we could observe galaxies that to about 46 billion light-years away, accounting for cosmic expansion. But galaxies beyond a certain distance, the cosmic event horizon, are receding faster than light to reach us. As space expands, this horizon shrinks. Galaxies currently visible will cross the horizon and disappear from view. Their light will be redshifted to infinity, stretched to wavelengths larger than the observable universe. Within about 100 billion years, every galaxy outside our local group will have crossed this horizon. The local group, gravitationally bound by mutual gravity, will merge into a single massive galaxy. When future astronomers in that merged galaxy look out into the cosmos, they'll see nothing. No other galaxy. No cosmic microwave background. It will have been redshifted to unmeasurably low energies. No evidence of the Big Bang. They'll see a static universe consisting of one galaxy surrounded by eternal darkness. They'll have no way to discover cosmology, the Big Bang, dark energy, or the cosmic web. The evidence will have literally expanded beyond their ability to observe it. The cosmic web fragments first, then the evidence of its existence disappears entirely. What will happen within our local group during this? The Milky Way and Andromeda galaxies are currently approaching each other at about 110 kilometers per second. In approximately 4 billion years, they'll collide. The collision will be spectacular, but not destructive to individual stars. The distances between stars are so vast that direct collisions are unlikely. Over billions of years, the two galaxies will merge, forming a massive elliptical galaxy sometimes nicknamed Milkomeda. The smaller galaxies in our local group, the Triangulum Galaxy, the Large and Small Magellanic Clouds, and dozens of dwarf galaxies, will also eventually merge into this structure. The result, supergalaxy, will be gravitationally isolated. No matter will flow in from cosmic web filaments. No new gas will arrive to fuel star formation. The galaxy will gradually exhaust its available hydrogen, forming all the stars it will ever form. Star formation will peak during the merger events, then gradually decline. Within about 100 trillion years, star formation will cease entirely. All the hydrogen will have been converted to helium and heavier elements, or ejected from the galaxy, or locked in failed stars called brown dwarfs. The galaxy will grow. Only long-lived red dwarf stars will remain, slowly burning through their fuel over trillions of years. Eventually, even they will fade. The cosmic web's final gift to our local group will have been the gas it delivered to us before the fragmentation. Enough to sustain star formation for 100 trillion years, but no more. The heat death zoom out to the ultimate fate of the entire cosmic web. In the far future, perhaps 10 to the power of 100 years, the universe reaches heat. This is the state of maximum entropy, where all usable energy has been expended and no more work can be performed. Stars will have exhausted their fuel. Stellar remnants, white dwarfs, neutron stars, black holes will dominate. Even these will decay through exotic process. White dwarfs will gradually cool to black dwarfs, frozen stellar corpses at near absolute zero. Neutron stars will cool similarly. Black holes will evaporate through Hawking radiation, a quantum process where black holes slowly lose mass by emitting thermal radiation. The largest black holes, at the centers of galaxy clusters, will take 10 to the power of 100 years to evaporate. When they finally disappear, they'll release one last burst of radiation into the universe before vanishing completely. The cosmic web itself will have long since dispersed. Dark energy will have stretched space to such extremes that in the nodes, the former galaxy clusters, will have expanded into diffuse clouds of isolated stellar remnants. Eventually, protons may decay. If certain grand unified theories are correct, protons have a finite lifetime of perhaps 10 to the power of 35 years. When protons decay, all atoms will disintegrate. The cosmic web, which once held galaxies together across billions of light years, will dissolve into an infinite ocean of elementary particles and radiation, spread thinner than the thinnest fog, approaching absolute zero temperature, eternally expanding into the structure that enabled everything. Galaxies, stars, planets, life, consciousness will be gone, erased by entropy and expansion. But heat death isn't the only possibility. The cosmic web's fate depends on the nature of dark energy, which we don't fully understand. If dark energy is precisely Einstein's cosmological constant, truly constant over zero, then heat death is inevitable. But if dark energy changes over feed, other futures become possible. Scenario 1. The Big Rip. If dark energy strengthens over feed, expansion accelerates ever faster. Eventually, expansion becomes so rapid that it overcomes gravitational binding at all scales. Galaxy clusters are torn apart, then galaxies, then star systems, then planets, then atoms themselves. Space expands faster than the forces holding matter together can resist. The cosmic web is shredded to subatomic particles. This could occur as soon as 50 billion years from now. Scenario 2. The Big Crunch. If dark energy reverses, becoming attractive instead of repulsive, cosmic expansion could halt and reverse. The cosmic web would begin contracting. Filaments, nodes would merge. Eventually, all matter would converge toward a single point. the universe collapsing in a mirror image of the Big Bang. Some theories suggest this collapse could trigger a new Big Bang, creating a cyclic universe where cosmic webs form, expand, contract, and reform eternally. Scenario 3. Vacuum decay. Quantum field theory suggests our universe might exist in a metastable state, like a ball balanced on a hilltop, stable for now but vulnerable to collapse. If the vacuum state decays, a bubble of true vacuum would expand at the speed of light, destroying everything in its path, rewriting the laws of physics as it spreads. The cosmic web would be erased as the bubble passes, replaced by a new form of space with different physical properties. Life and structure as we know them would cease to exist. The fate of the cosmic web and everything within it remains uncertain. Here's a final thought about the cosmic web's fate and significance. Even after the cosmic web disperses, even after heat death, even if vacuum decay occurs, the information about the structure that once existed will persist, encoded in quantum correlations, preserved in the subtle patterns of quantum entanglement. The holographic principle, a concept from quantum gravity theory, suggests that all information in a volume of space is encoded on the boundary of that region. Even after the cosmic web disperses, the information about its structure might be preserved in a cosmic horizon, like data on a hard drive. If the universe is infinite and eternal, then somewhere, somehow, the pattern of our cosmic web, the specific arrangement of filaments and nodes, the distribution of galaxies, the evolution of structure, will be instantiated again. In an infinite universe, every possible configuration of matter must occur infinitely many times. Our cosmic web isn't unique. Somewhere, infinitely far away, there's another cosmic web with the same structure, the same galaxies, the same stars, the same planets, the same civilizations asking the same questions about their place in the cosmos. The cosmic web is eternal not because any individual instance lasts forever, but because the pattern repeats infinitely across infinite space. Structure arises, structure evolves, structure disperses, but the information, the pattern, persists. We've journeyed through 120 minutes exploring one of the universe's most fundamental structures. We began with a simple observation. Galaxies form patterns. We discovered that these patterns reveal an invisible scaffolding of dark matter, the cosmic web, that shapes everything we see. We've learned that the web formed from quantum fluctuations in the first moments after the Big Bang, that it grew through gravitational amplification over 13.8 billion years, that it channels matter along filaments, concentrates it in nodes, and leaves vast voids nearly empty. We've seen how the web determines where galaxies form, how they evolve, and ultimately where life-friendly environments can exist. We've confronted mysteries, anomalies in cosmic structure, puzzles about dark matter's nature, questions about the webs. We've looked forward to the far future, seeing how the cosmic web will fragment as dark energy drives cosmic acceleration, isolating each node into its own island universe, eventually dispersing all structure into maximum entropy. But the deepest insight is this. The cosmic web isn't just structure, it's meaning. It's the pattern that emerged from chaos, the order that arose from quantum randomness, the scaffolding upon which complexity, chemistry, and consciousness became possible. Every atom in your body traveled along cosmic web filaments before arriving on Earth. Every thought you think occurs within a galaxy positioned within the web's arc. Every observation you make, every time you look up at the night sky, you're seeing the cosmic web's legacy. We are the universe becoming aware of itself. And the structure we've become aware of, the cosmic web, is the foundation of everything. The web connects all matter across cosmic distances. It connects the past to the present, it connects the quantum fluctuations of the infant universe to the galaxies we see today, to the heat death trillions of years hence. In understanding the cosmic web, we understand our place within the largest structure that exists. A pattern of matter and energy spanning the observable universe, holding everything together through invisible threads of gravity. The night sky isn't darkness punctuated by random lights, it's a view of the cosmic web, a vast architecture of structure and void, connection and isolation, spanning scales from quantum to cosmic, from the Big Bang to the far future. We live within the web. We're made from the web. We're beginning to understand the web. And in that understanding, we find perhaps the most profound realization of all. The universe is not chaos. It's architecture, pattern, structure, connection. The cosmic web proves that even in the vast darkness of space, everything is connected to everything else. We are not alone. We are isolated. We are threads in the greatest tapestry ever woven. A web of dark matter and light, spanning billions of years and billions of light years, connecting every star to every other star in an infinite network of gravity and history. The universe is vast. The web is eternal. The journey continues.